hands, who in here has actually ever heard of flow-based programming before? One. All right. Two. Who's? Okay. So have you guys actually done any flow-based programming? Okay. All right. So a couple of shameless slides. I work for the World Table, and we're building reputation on the blockchain. Part of that is an open reputation platform, open source platform. Yeah. Can you hear me?
I can hear you. We actually do have a microphone on.
I got something on here. Is that?
Oh, as long as it said it was recording, I think we're good.
How do I know that it says it's recording?
Oh, sorry, I didn't mean to interrupt you.
It's all right.
Yeah, it's recording.
Okay, great.
Thank you.
All right. Good. The idea is to use reputation to modulate any internet interaction or transaction. I'm also the developer of a flow-based programming framework called IOFlow. It's actually currently used in another open source software stack called SaltStack. Familiar with that? So let's talk about flow-based programming. What is flow-based programming? It originated in the 1970s, so it's a contemporary with functional programming and object-oriented programming. It's been around for a very long time. The problem is that it wasn't really compatible with writing languages. Academics didn't write frameworks in those days, they wrote languages. So flow-based programming really is naturally best expressed in a framework. It's relatively unknown, but there's been a lot of interest lately. If you want to think about flow-based programming, one of the ways to think about it mentally is general purpose data flow programming. So data flow programming has been around for a long time, typically used in signal processing, graphics, high performance computing. So if I wanted to use those sort of constructs, but for general purpose programming, then data flow programming is what is the difference. It's typically a programming style, pattern, or framework, not a language. And that's the point of this talk, is to give you the mental model of what flow-based programming does so that you can use it in architecting software that you may not be using directly as flow-based programming. Because it's a different mental concept that is really useful in today's modern age of concurrent, asynchronous, distributed applications. Because that's what flow-based programming is best at. It's a simplifying, unifying paradigm. And I'll show you an example of that later on. And like I said, distributed concurrent applications benefit most from a flow-based programming style. And it can be useful even when you're not using a flow-based programming framework. And I'll show you. And the thing is lots of people already use flow-based programming, they just don't know it. So let's look at some of the resources. Wait, did I miss that? There we go. There we go. Flow-based programming, from a philosophical point of view, shares a lot with what are called port automata. And so there's a really good paper by Steenstrup and Arvid from 1982 that talks about the philosophy, the design of port automata and concurrent processes. So that's why it's really good for concurrent systems, because it is designed for that. And then a more recent paper is software components for real time. If you want to learn about flow-based programming, there's a book. It's kind of a very dense, academically written book. Paul Morrison, who coined the phrase flow-based programming, he has a website, and there's some external links on there and some resources so you can get a really good sense of what it looks like outside of this. So let's look about some of the frameworks. In JavaScript, something called NoFlow. They recently had a big Kickstarter campaign, raised a lot of money. Facebook has something called Flux. It uses React components and allows you to integrate them in a flow-based programming framework. There's another one called constructible.es. In Python, IOFlow, that's the one I've written, is in Python. There's something called pipes. Another one called HighFlow or PIF. Other frameworks include Expecto, and then there are some port-based object frameworks. Port-based objects are used a lot in robotics and real-time control systems, but they are of the family of flow-based programming. And then we have some frameworks that are more or less flow-based programming. Apache Storm, it's more on the data flow side, but it is definitely in the family of things that use the flow-based programming paradigm. IBM InfoSphere Streams, Microsoft Azure Event Hubs. If you're starting to get an idea of the sort of concurrent real-time web, right? You want to build a real-time web, you've got real-time data that you're streaming, that you're putting out there, and you want to build applications that use that. In the robotics world, something that's very popular is called the robotic operating system. And it's definitely a flow-based programming type paradigm. And in fact, flow-based programming, really, the most successful uses of it over the last 20 years. Only recently have people started using it for web applications. We're in robotics applications. And that's actually where I started using it 20 years ago, was because I was a robotics person. Because you're building concurrent real-time applications. And you've got multiple robots with multiple sensors and actuators and processes and software things and communications all going at the same time. And you have to manage this complexity. And flow-based programming is the natural way to do that. Some other ones, MATLAB Simulink, LabVIEW, and Erlang is very flow-based programming like. So what is it? At its essence, you have black box behaviors. Think of a black box. You've got a piece of software that's a black box. It has inputs, it has outputs, and you may also add parameters as inputs. But the key is that you're transforming the inputs governed by the parameters into outputs. There's nothing inside the black box that you need to know about from a composition point of view, because everything's specified externally by the inputs and outputs. You can also feed back the outputs. So you can have state, but notice the state is external to the black box. It's not encapsulated or hidden in the black box. It's completely observable and traceable outside of the black box. And this is a key because this eliminates all of the dependency problems that come when you build complex systems where you've got, hidden state, right? So all the functional programming people in here, flow-based programming leverages the idea of no side effects, right? So it has functional program-ish like behavior. So you can now think about a behavior that transports its inputs, past outputs, governed by parameters into its outputs. So let's look at what we do when we program, right? We take these behaviors with externally specified inputs, outputs, parameters, and we compose them declaratively into networks and graphs of behaviors. And because each behavior is independent and completely specified by external inputs, outputs, and parameters, it can be recombined endlessly. 100% code reuse. There is, you get it for free. So when you think programming, you start to think, okay, I want to build something complex. I build components or behaviors that are transformations. I specify the inputs, the outputs, and the parameters, and now I just go to town, putting those together. It's true plug-and-play programming. OOP, object-oriented programming, wanted to do this, and it went off on a path that kind of didn't ever come back. The original books, like Cox wrote one of the original books, called it Software Components. Original books, the guy who invented Objective-C. His goal was to build what he called software integrated circuits. Basically, black boxes you could plug in and have 100% reuse. And somewhere along the line, it became something else. So, think about this. programming is data flow oriented plus component oriented. So that's where it goes from data flow to where we've got these components. If you think about it, the data flow part is functional programming, right? We're flowing data. It's all apparent. There's no side effects. There's no hidden state. It's also object-oriented program-ish because I have components that I can stand up and compose and put places. The difference is the components don't have any hidden state. So we want to go from this to this. So this is a variant that starts to look like what you might be familiar with. So what we've done is we've taken this network graph of sort of ephemeral inputs and outputs and put them into a data store substrate. So we still get all of the benefits of the flow-based programming, but we add the fact because they're in this data store, we can trace them, we can observe them, we can configure them. So what's a framework look like? It's analogous to a web application framework. What does it do? Typically, a framework provides syntactic sugar and/or graphical editors. So, for example, IOFlow has a graphical JavaScript editor for editing that. Same thing with, they also have a language. Flux has a language, syntactic sugar. So this is what Flux looks like. You build a web application as a flow-based programming graph. And then this is an example of a flow-based programming language or configuration language. That's actually IOFlow on the side there. Well, don't read it right now, just give you an idea. The thing is that with a flow-based programming framework, you end up already where many distributed application architectures are trying to get to, because you've already built the system with isolation, with message passing, and all of those things are built in at the low level. So let's see how this relates to the dependency inversion principle. Who's heard of the dependency inversion principle before? Okay, so this isn't new, right? It starts off, the main idea is we can all tell what bad software design looks like, right? That's easy, right? It's rigid. It's fragile. It's immobile, right? We can all tell. It still functions, right? It still works, pass all your unit tests, you can ship it, but as soon as you want to change something, you're making lots of changes. As soon as you want to change something, things break. You want to have reuse, a lot of disentanglement going on, right? So dependency inversion principle says if you're programming in an object-oriented programming paradigm, what do you have to do? You have to start doing things like this. High-level modules do not depend on low-level modules. You have to break it up. You can't just have a high-level module call a low-level module. What do? You have to create an interface, an abstraction, so that the high-level module calls the interface. And then the interface provides the call to the low-level module, so that you can swap out the low-level module for a different module, because the interface is the dependency, right? So you're creating dependency management where you're separating your modules using another layer, right? Abstractions should not depend on details. So I don't want to build interfaces that are specific. I want to build interfaces, right, that are abstract, and want the details to depend on another layer on an abstraction. So I want to take my object-oriented programming paradigm and add interfaces everywhere. And if you're a Java programmer, is that your life, right? Who's a Java programmer in here? You, right? You live for Maven, right? Right? You want interfaces everywhere. If you're Ruby or Python, you avoid most of that. But you still have to deal with the issue of module dependencies. So the key is, it's all about dependency management. If you want to build complex applications, you want to manage dependencies. So what's the best way to manage dependencies? Well, let's see what happens. Take the same set of things. Now, what do we do with, how does flow-based programming address this? It transcends this principle. Why does it do that? There are no modules, just components. There are no abstractions or details, just data. Components depend on data, not other components. One dependency, data. That's the only thing you're dependent on. Everything's dependent on data. You change the data, behavior system changes, yes?
You have to be dependent on the metadata, the format of the data.
Yes, right.
So it's not just the data that you're dependent on.
Yes, well it is. The metadata, the format of the data, that is the dependency. It isn't modules or how modules are organized or the links or identities or references to objects. You don't worry about references to objects. You just worry about data, right? And metadata, you know, the structure, the schema of the data, it's all about the data. It's very declarative, right? You define the data, you're done. Define the data, and then you define the network and the graph, which is also data. And then the components are completely plug and play. So think about this. This is what your mind wants to think about when you're programming a data flow programming. You're thinking of data. You've got a data substrate, and you're going to plug behaviors into that data. Those behaviors transform the data. So what this gives you is what's called replacement independence. Behaviors can be externally connected without any internal changes, right? Mobility, rigidity, fragility, gone away. Right? Composition of complex network graphs is conceptually simple because you're just building blocks of transformations. You know what you want to transform. So if you're a functional programmer, this is how you think when you're functionally programming. You're transforming, you know, the data, the arguments to your functional parameters. You're doing function chaining, right? A function chain is really another way of flow-based programming. It's just that it's all in a language, right? So it's not abstracted out. It's not externally connected. It's built into your program. You can't. It's hidden, right? Because partitioning, and this is the key. This is where it works for distributed applications. Partitioning occurs at the behavior level, which is intra-process, intra-host, not inter-process, not inter-host. We're forced in modern programming paradigms to do flow-based programming when we want to leave a process or leave a host, because we no longer can write code that spans those boundaries. So what do? We do message passing. We do some form of inter-process communications. We do internet messages. We do REST interfaces. All of those are ways of building external dependencies and communication paths between components because of the hard barrier that the process and the host provide. But with flow-based programming, you build that in at the lowest level. It doesn't matter where the boundaries are, because you've already built the boundaries at the component level. Placement independence means you minimize the dependencies that you have to keep track of. You get flexibility, robustness, and mobility. So let's look at a meta-architecture pattern. So we've shown this diagram 2 or 3 times. Now let's look at some other diagrams that you're familiar with that look just the same. Just organize them, change your mind. Okay? Pub sub, right? This is pub sub. What have I got? I've got publishers and subscribers. Those are components. They send data, right? Network messages, events, to a data substrate, the pub sub hub server. It's flow-based programming, right? But I forced my boundaries to be at the internet level, at the host level, not at the component level within my code. Message brokers, same basic architecture. Backend as a service, right? You have a data substrate. You have clients. They send data, JSON data, to and from this backend database, real-time updates. It is essentially recreating flow-based programming with a paradigm that people are familiar with. But it's still at the inter-process, inter-host level. Microservices, very similar approach. Break it up into small pieces, have externally defined dependencies, REST interfaces, URLs, so that you can build and compose your application as a set of behaviors that interchange data. That's why I say it's a meta-architecture pattern. You got enterprise service buses, same thing. So all of the distributed application architectures can be thought of as the same pattern. That is, components exchanging data through a data substrate or some sort of bus. So let's think about complexity management. What is real complexity? The way I look at complexity is that it's the dependencies. There are lots of complexity measures that people use for software. One of them is dependency. And I think that is the most important one. So if you count up the number of dependencies in your software, it's a really good measure of how complex it is. The more dependencies you have, the harder it is that it's going to be able to change your software, add different functionality. Apparent complexity are the number of dependencies that you must manage in order to make changes. So you could have a really complex system that has lots of underlying dependencies, but as a programmer, if you don't have to manage those, if you don't think about those, you can do really good stuff. This is expressive power. Do you have a framework that allows you to that has low apparent complexity? Because it's the ratio of those two that determine how good the architecture is. So perceived risk, right? As a programmer, what's the perceived risk? If you are faced with making lots of changes that could break things, you're afraid, right? You know, it's scary. You don't want to break stuff. And so the ability to make meaningful enhancements to your software is a function of the ratio of the apparent complexity to the real complexity. So here's a graph. This is really a cartoon, but this actually reflects what I went through early in my career when I was building autonomous vehicle system software. What I found is that different architectures have different levels of scalability. Now the thing is, if you're down here where the amount of capability that you have to provide is small, the total complexity of the system is small, it doesn't really matter what architecture you use. You can use Java, you can use Python, you can use functional programming, you can use object-oriented programming, you can use whatever you want, right? You can argue all day about what your style is, how well it works, and they all work. Because you're not complex enough for it to matter. But what happens is that as you start adding complexity, the ratio of apparent to real complexity gives you this curve. And if you've got an architecture that doesn't scale well, you'll hit a wall where trying to make one improvement or a few improvements is so complicated that you just want to start over. You're just saying, we can't make anything. We have to throw it all away and do something. And I did this. I had an architecture, worked on it for about a year, wrote a bunch of code, had some vehicles running with it, and we hit the wall. So we switched to another one, right? Just did the same thing for another year, hit the wall. Finally, we said, this isn't working. And so we switched to a flow-based architecture and never hit the wall, right? It just scales. So when you're building a distributed application, think of all the things you have to put together. You have to have some sort of message broker, pub sub hub, a task scheduler, database, key value store, a resource manager, maybe a data flow processor, maybe a bunch of services. You have to put all these moving parts together and try to make them work as an application. That is very similar to what you have to do in an autonomous underwater vehicle. So these are some of the vehicles that are designed and developed. This is back in the 90s. Some more recent ones, just showing some of the sort of missions. The thing is, each one of those vehicles is like a menagerie. You've got lots of services, you've got lots of data sources, lots of data sinks, you've got current processes running, you've got all sorts of systems, building, shipboard automation, similar things. This is an example of a controller for, I think this is the pitch plane controller, expressed in a data flow architecture, flow-based. That enabled us to build, complex controllers that we could change, that I could have graduate students work with and not worry about losing the vehicle. When you put a $500,000 vehicle in the water and you can't talk to it, and you're in the Gulf Stream that's going at pretty fast pace, and if you have one bug in your software and it heads east, you'll never see it again. And it's kind of scary every day to put a $500,000 piece of hardware in the water and think that you might not ever see it again. You have a different approach to writing code, right? So that's how I said I have to really build software that is robust, scalable, dependable, and I have replacement independence, so I can change stuff and not worry about breaking things. So I'll give you an example of FlowScript, which is the IOFlow programming language. It puts all these things in one place. It gives you scheduling and execution, PubSub, messaging, observability, traceability, and nested concurrent context. It's a line-oriented, contextual, declarative configuration language, not block-oriented. So I'll give you an example. As a verb with an optional object and optional prepositional phrases. So for example, done would be just a verb. Frame, build, and setup would be a verb with an object and a prepositional phrase. Set speed to 5. Here's one with a few prepositional phrases. So basically these are parameters. The standard one for building custom behavior is the do verb. So you might look at some, so that's actually running a particular behavior in a flow-based programming. Now, one of the things that is useful in building these sorts of systems is context management. Who's familiar with Python? Okay, so with statement. What does the with statement do? Can you tell me what the with statement does?
Does that set the scope of a variable?
No, it's a context manager. So like if I want to open a file, right, I can with, open as, and then in that block, whenever I leave that block, the context manager that I invoke at the top of the block makes sure the file gets closed before I leave. Right? And I can have multiple context managers, I have nested context managers. So when you're building real-time applications, context is important. Managing context is really important because you're managing resources. And if I don't clean up my own mess, some other process, someplace, is going to want to interact with that resource, and I didn't clean it up. So the resource is in an uncertain state. File is still left open when it should have been closed, right? A stream is, didn't get opened correctly or closed in the wrong way. So think of not just context management for external resources like files and network processes. Think of context management for everything you do when you program. For every resource, every memory location, everything that you might do, you have a context and a context manager for it. So in FlowScript, the metaphor, and I like doing this, and sometimes people laugh at me for it, but I like using program metaphors where I make up terminology that doesn't have baggage with it. So I'll just use terms that evoke a certain meaning in the context I'm using them in, but I use this example, right? If I'm a Java programmer and I want to create something to store birds in, right? In my software, I call it a flying bird cage, right? But for me, I would call it an aviary, right? Just a different approach, right? It's a word that means the same thing without being 10 pages long. So in IOFlow, a house is the context for the data substrate. Anything in a house shares the same data substrate. A framer is a concurrent process, but these aren't processes. These are actually weightless threads. So it's like for the Python and Ruby programmers, these are next. You're not actually doing a process. You're using a yield statement to yield context. So these are coroutines. Frame is actually a context for executing actions, and frames can be nested. So I can have arbitrarily nested frames. The other types of context is an actioning context. An actioning context is inside of a frame, but now I have lifecycle context. And this is more like the context manager that you're thinking about. So I have an enter, a recur, and an exit. Those are three. There's actually 7, but these are the 3 basic ones. So when I enter a frame, I do whatever things that I need to do to set up the frame. As long as I'm in the frame, I recur, and when I exit, I clean up my actions. And so I can arbitrarily build components and put them in those contexts, and that determines how they get executed. So hierarchical state, what does that give me? This is an example of a state machine. This is a flat state machine. If I'm building concurrent systems, you end up writing state machines. Sometimes people write state machines and never actually diagram, and then they wonder, well, why did this happen and this happen? And the order of events didn't make sense, and the state changed, right? Well, one of the reasons people don't write state machines is a very simple state machine gets really complicated pretty quickly, right? So they really tend to avoid writing state machines. So this has got 9 states. The transitions between states are colored. So if a state transitions to another state, they all have the same color. So the reds are transitions to state A, purples are common transitions to B or C, the blues are common transitions between states. Now if I wanted to rewrite that as a hierarchical state machine, it gets a lot simpler. What I've done is I've subsumed a given state into a superstate with common transitions. So if you think about it from a code perspective, if I'm doing a transition, what does a transition look like in code? Well, it's conditional. If X, then Y, right? If X, call a subroutine. If X, change your context, do something, right? So every transition is some sort of if, then block. And if I have common transitions, then I have duplicated code. So I'm not very dry. So if I have a hierarchical state machine, I'm very dry. I get rid of all the duplicated code because the common transitions occur in the higher level states. Another way to represent a hierarchical state machine is as a tree, where the superstates hold common behaviors, common actions, and substates hold more specific ones. So let's see what it looks like if I have a transition. This is what a transition looks like in FlowScript. And I've got this hierarchical state machine tree. So if I'm in state G, I'm also in X and Z. If I want to transition to F, I'm going to transition out of the non-common states and transition into the common states. Transition out of the non-common, transition into the non-common, and the ones that are common, I don't transition. So for example, F and Y are new, but Z is common. Oops, did it? No, I guess it messed up. I think I lost some of my... That was weird. Sorry about that. I think I lost some of my animation there. There we go. Oh, the last one got missed. Oh, there it is. I just can't see it from here. Oh, okay. All right, so you see, so I don't transition out of Z, I transition into, I guess it's just the angle, I can't see the thing. So one of the keys is that the priorities are dichotomous. Transitions, the priority is top down. Actions, the priority is bottom up. So in a conventional object-oriented programming framework, everything is bottom up. Subclasses override superclasses unless you explicitly call the superclass. Transitions should be top down because I want to be in a context when it's valid. If I have an event that occurs that says that I'm no longer in a valid context, then I want to transition. So I can put the higher level ones up high. This gives me the ability to create what's called a reliable services envelope. where I can put failure detection, things that affect the viability of my concurrent system in the high-level states or frames, and then mission-specific stuff or application-specific stuff in the lower ones. So we get incremental encapsulation. We have framing, gives us concurrency. We have auxiliary framers, master-slave framers. So we have multiple ways that we can achieve concurrency. We have nested frames, then we have actioning, we have components, we have flow strip verbs, we have built-in behaviors, and then you can custom code your own behaviors and components. So the data substrate, we want to have high replacement independence. So we have the ability to put things in the data substrate. The data substrate is a key value store that's hierarchical, uses a name spacing. And these are different types of addressing modes. I'm not going to go into a lot of detail with those. An example of something that's implemented on top of IOFlow is the rate, which is a reliable asynchronous event transport protocol that's actually used in salt stack. So I went through a lot of stuff pretty quickly, because I talk fast. I can show you some code, or I can answer questions. What would you guys like to see at this point?
I'd like to see code.
Yeah, like code.
Like to see code. Okay. This is IOFlow. Give you an example of a very simple. Let's see. Here's a really basic flow script. And this is actually so I have a bunch of examples, or robotic examples. They're really simple. And then I have some more complicated ones from some other applications. So let's see what this does. So it defines a house. Can you read that? Or do I need to make that font bigger? Can you read that? Good enough? Yeah, okay. So, first statement defines the house. Init is a way of initializing anything in the data store. And then I have a framer. Think of a framer as a process. Now, it's not really a process. Right? There is a scheduler. So those of you familiar, anybody here familiar with G-Event? Or G-Event? Twisted? Twisted? Let's see. I guess some of you are Node.js guys. Right? so there are several approaches to asynchronous execution that don't involve threads or processes. So one is the reactor pattern. That's what Node uses, Twisted uses. And that is where you have a scheduler. You register a callback with the scheduler. When an event occurs, you call the callback, right? Promises are an example of the reactor pattern. Another pattern is what G-event does. G-event basically has the same thing as a scheduler, but you create these micro threads that execute as if they were threads. So you have an infinite loop and you sleep. And whenever you sleep, you give control back to the scheduler. So you can write your code the way you would if you were writing processes or threads. You have sleeps, and when you do an I/O call, it blocks your thread, but it's really a non-blocking I/O, so it doesn't block the scheduler. And then the third type is a flow-based type. And in flow-based, you don't have these threads, you don't have these loops, you don't have callbacks. You just have a scheduler that executes the components. Whenever they have data, you execute them. And so IOFlow uses this approach. And so a frame is just a context of action. So whenever the scheduler runs the framer, it runs the current frame. And these are the actions in the current frames. These are the behaviors. And so, for example, I'm sorry, is there a question?
Yeah, so, you know, your other previous diagram had a data substrate. Is that the step on line 6, or am I thinking of something else?
Line 4 is writing something to the data substrate.
Okay.
Line 6 is defining.
The condition is...
No, it's defining a scheduling context. So part of the thing is I didn't show you scheduling context. So the FlowScript language allows me to basically build the frameworks. So I can build the networks of behaviors, specify what order they run in, and all in one place. So a lot of flow-based programming frameworks actually hide that from you. You don't actually have control over the execution context. So like NoFlow or Flux, you can define the network, but you depend on the scheduling to just happen magically. And FlowScript actually gives you explicit control over the scheduling. So you specify the framework and the scheduling in the same place. So frame start, so this says this framer is the first frame that it's going to execute is start. And so each of these is a behavior. And some of these are built-in behaviors, so they have built-in verbs. And if I have a do, then what that is saying is, do whatever behavior is defined by this. And then go is a transition. And so in this case, this frame is just going to execute these, and then it's going to transition to the next frame. And then I have frame do slave, which is going to control another framer. So now I've got one framer controlling another framer. So I've got concurrent execution, I've got high-level hierarchical stuff. So there's a lot of capability here, and I probably picked a more complex example than I thought I wanted to pick. Let me try a different one. We got some other stuff in here. Let's do, this one's simple. There we go. This is simpler. All right. So in this one, I have a simulator that is simulating the motion of an underwater vehicle. I have a mission that basically causes the vehicle to go in a box. Okay, so the north leg, the east leg, the south leg, the west leg, and then stop. And then I have an autopilot that actually runs the control stuff. So I've got really 3 concurrent processes happening at the same time. They all interact with the same substrate. When I set the heading to 0, and I set the elapse to 20, this go transition will go to the next one when the elapse is greater than the goal of 20 seconds. And in every case, it does the same thing.
How is elapsed? How is elapsed implemented?
Elapsed is a special one in this case. It's actually, every time the framer runs, it sets elapsed. So there's some special ones like like elapse, the number of times. These are syntactic sugar to make it easy to do time behaviors, right? Because you're doing scheduling, so sort of built-in scheduling. So let's run this guy and get an idea what it's like to run it.
And then maybe you can show us where it's wired or
Yes, yeah, absolutely, absolutely. So that was it running that mission. Oops, I didn't want to do that. Okay, so now it's running in real time. So let me show you what it did here. So it's got debug on, so I'm just running the IOFlow executor. So this is it parsing the IOFlow script, so it's saying what the script is doing. And then it just updated. So it's building the house. It's showing you each of the lines as it's parsing it. It built the house. These are the data associated with that house. All of these things are in the metadata, and every time it updates this, it's transitioning to a different frame. So this is running in real time. It's taking 20 seconds. Every 20 seconds, it's going to move to a new box. Whereas the first time I ran it fast in real time. This is it resolving all of the references, and then this is the data store. So these are the nodes and shares in the data store. So think of a node like a directory, and a share is like a file, right? But the files are really just key value, they're just dicts. It's just a nested key value store. So we can see, for example, in Framer vehicle sim. These are the data that get created for Framer vehicle sim. We also had a Framer simulator. We also had controllers. So this is where all the data is in the data store. So each of those behaviors create when it got fired up and built the data and put the stuff there. So we have Framer vehicle sim, Framer mission. Here's elapsed. So there's that elapsed value for that Framer. Recurred, active. That's the active. So right now the active frame was mission stop at the time that this printed this out. It looks like, oh yeah, and this printed out at the end of the mission. So the mission completed. So here's the mission, just showing the transitions. So let's look at something a little more less robotic-y and more system software. So this is Salt Stack, and here's the Salt Master flow script. So Salt, the 0MQ version of Salt, starts up with at least 9 separate processes. It runs 9 separate processes. The IOFlow version of Salt has fewer processes. Unfortunately, it has to have more than one because there are parts of salt that are not concurrent process friendly. They have to be in their own environment. But this flow script schedules all of those, sets them all up and runs them. So what's happening here is that this is the framer for the rate UDP communication stack. And then there's a setup frame. Here we see the enter context. We clean up, this is cleaning up some data that the rate stack leaves on the disk. It sets up the stack, which sets up the IP address, stuff like that. So this do salt rate road stack setup is a behavior. All right, so let's go find that behavior. Right there. So here's the setup behavior. And this action method is what happens during setup. So all of the code for setting up the stack is right here. This is the behavior. So this is a fairly complicated one because it's doing a lot of work to set itself up. But I can run that behavior anytime by just changing the flow script and run. So here's some other behaviors. Here's a simple one. Salt rate road cluster. Basically, it's just updating the cluster mode. Basically, changing something in the data store. Here's another one that's fairly simple. Ushers are if I have multiple masters and I want to configure the multiple masters. So this is reading in from the ops dictionary, the cluster mode, and then calling a function to get the masters out of that dictionary. So it's just parsing that. And then it sets that in the value. So it's basically taking stuff from this ops, transforming it with this call, and sticking it in ushers. So it's a very simple, take the data, move it, put it someplace. And this behavior gets called by the flow script schedule, calls the action method. Anytime that behavior shows up in the script, it calls this action method. So I'm just building components. And there's also a decorator. Salt didn't use a lot of the decorators, but there's a decorator, so I can just have an action method like this and decorate it, and it becomes a behavior. So it's very similar to like Flask or Bottle or some other web framework. I don't think it uses any decorators in here. There's another project where it uses the decorators. Decorators were added a little bit later after a lot of this code got written. So all of the behaviors show up in this file, but in here is where they get executed. So 2 pages is the complete salt master code. And if you look at the 0MQ code, it's multiple pages of dense Python code.
When it starts to set up and does the enter stuff like in a row and then it fires off 0 and 2 start and spawn me that goes concurrently to 2 separate.
No, go is a transition. So this framer then transitions to 0MQ start. And then it
Maybe just wait for that to come back before it goes to spawn me, or it fire goes off concurrently.
well, actually, something that I didn't cover. See this let right here? That let is called a before enter action. It's the equivalent of a guard. And so it's a precondition. If that is not true, it won't enter into that frame. So basically, it calls 0MQ start. It will never go to 0MQ start unless salt at set of 0MQ behavior is true. And so one of the things that this is doing, this is something that was added much later because they wanted to have the master be able to support both rate and 0MQ communications. So it's firing off another process to manage 0MQ, so it's doing both. So now we've got IOFlow controlling both of those. But in the case that it can't enter that one, then it will go to spawn main, which means it just ignores it. And so spawn main, but you see in 0 and Q start, is going to go to spawn main. So basically, it's a fork. It's a logical fork in the process. It's going through. I'm going to do the things in frame setup, and then if I want to do 0 and Q, I'll do 0 and Q start, and then go to spawn main. If that's not there, then I'll go directly to spawn main. And then it runs the rate main fork, and then it goes to spawn workers. In spawn workers, it does the worker fork, then it goes to start, and then in start, it just finishes starting up. And so this frame start just starts up all the other framers. So bit start is starting a framer. So now what I've got is a frame that is controlling all of these other concurrent framers. So I basically have arbitrarily complex, nested, concurrent processes that are all running in a single process. Logically, I have total logical concurrency without having to spawn processes and worry about, sharing resources, because they're all in this same thing. So this is an example of a fairly complex application, but there's a world in between, and we'll run out of time. So
Is there like, there's like a little Python interpreter that reads this file?
IOFlow,
Yeah.
right. So IOFlow is written in Python. It reads this file, parses this file, builds the network, right? Like I said, programming is building a network or graph of behaviors. So IOFlow is the syntactic sugar that just builds it for you. So your programming is, once you have the behaviors, you just write flow scripts. These are just declarative scripts that say, I want this to run in this context. Whenever this context runs, run this. So, yes?
So are behaviors just Python classes that have a certain
Yeah,
interface?
in this case, that's right.
Hey, how's it going, man?
Good. But not in all cases.
Huh?
Pretty good.
Not in all cases.
Well, no, if you use the decorator creates a class on the fly and does all that.
So behaviors are defined in Python. The flow script is used to generate the graph.
That's right.
Right? So that's the one side of the data
Yeah.
that you described. And then the other data is the substrate.
The substrate.
And the interface of the contract that the behaviors adhere to doesn't know about the
Anybody else?
organization of the data, right?
It does not.
It's just the internal.
It just knows that my inputs and outputs are these things.
So this determines what gets input to the behavior.
That's right.
The behavior doesn't directly access the behavior.
Well, it can, but it just depends on. There's different ways of. So you can build into the behavior like a fixed interface if you want to, or you can make it a variable interface. And so some of the stuff here had a fixed interface just because it was easier for people to understand when they were writing it, because I didn't write all this. But if you look in the flow script, if you see this per right here, per inode, that says all of your inputs and outputs are going to be referenced off from this relative path into the data. So I can define relative references, and then when it actually compiles the network, it says go to this place and get the data. So I can namespace all my data. Sorry, you gotta go.